Should I begin? Okay, so today's lecture is going to be about loops. But before I begin, I just want to announce that there's going to be a tutorial today where I'll answer questions and show you how to do the homework. In particular, you're going to see, I'll show you that to do the homework, you don't have to do infinite numbers of diagrams. So, right, the homework, the key problem is to do the tree-level amplitudes to arbitrary numbers of legs. But it's actually a very simple problem from the point of view of how many diagrams you have to work out. The answer will be one diagram, and I'll explain how that works. Yeah.
Probably missing something simple, but yesterday in the outline lecture number 2 was supposed to be trees. So
yeah, so that's trees are done.
so
Today is loops.
was given already?
What's that?
Is now, are we in lecture number 3 now?
No, and this is lecture number 2.
Okay.
Yeah. So today I talked. Yeah. So lecture 1 was trees. Lecture 2 will be loops. Lecture 3 and 4 will be lots of loops. And but the way we get to lots of loops is by working on the simplest theories you can, namely the n equals 4 super Yang-Mills. You know, as you heard, it's the hydrogen atom of the 21st century. So we're going to work out some very high loop orders in n equals 4 super Yang-Mills and n equals 8 supergravity on the blackboard. Okay, so actually also Nima is going to talk a lot more about n equals 4 super Yang-Mills. Here what I want to talk about are loops generically for real world theories like QCD, and the types of problems I want to talk about is how to do something that you need for colliders, like quarks, and there's a Z, and then gluons. The gluons then go into what's called jets. Along the path of the gluon, you get a hadronization and a spray of particles. Those are the jets. And how to do this. Now, obviously, a problem like this, you know, people spend their lives doing this. This is quite a non-trivial calculation from the point of view of Feynman diagrams, and even from the methods that I'm talking about, there's a lot of subtleties and things you have to worry about with dimensional regularization. So I am not going to work all of this out on the blackboard. In fact, I will skip all sorts of things. As I do my lecture, I'll just start asserting things. Oh, well, there's a theorem that says this, and oh, ignore that piece. It's not important, even though it is important. But the idea is I'm going to show you how the calculations really work. If you actually do the calculation, how the computer codes that do the calculations for the LHC, the modern ones, how they work, I'm going to show you in detail at least how certain pieces work. And then, unfortunately, it can't be a homework assignment to do in an afternoon, but then the basic ideas you can, in principle, can be applied to the rest of the pieces. You know, obviously, in 90 minutes, I'm not going to make you experts in loop calculations, you know, for the LHC, but I think I hope at least to give you a flavor of the ideas that go into this, the modern ideas. Now, the first thing you may notice, I wrote down a Feynman diagram, but that's okay. We're not going to calculate that thing. We just use it to, you know, so that I can tell you what it is. Yeah, even during the day, we're allowed to use Feynman diagrams. We're just not allowed to calculate them. Okay. Okay, so the general plan So first I'll give you an overview. And then the most important thing, I'll work out some examples. And these examples that I'm picking, I want to be clear about something. These are examples that had I told people, let's say 3, 4, or 5 years ago, saying, oh, I'm going to be in Jerusalem here giving lectures and working out these examples, it would be ridiculous. You know, you'd need some computer code that would generate hundreds and hundreds of pages of garbage before you could get these results. And I'm going to work out these examples on the blackboard, and, to really show you how it works. And then after a couple examples, then what we're going to do is I'll show you where it's actually applied, the types of problems that you can solve with these ideas that I'll be talking about. Okay, and these, of course, will be very complicated problems because you have to do better than 60 years of people doing calculations of this type. Okay, so that's actually rather non-trivial, but I'll give you an outline of the types of things that can be done today using these ideas. That'll be an overview of the state of the art. And this would be in collider physics. Like I say, today it's collider physics, and I guess it's maybe a week from now or so, I'll be speaking about supersymmetric theories. Okay, so the first thing is I'm going to quote a theorem, which I'm not going to prove. I'll just maybe say a couple words where it comes from, which the theorem then explains what problem we have to solve. Okay, and this is, let's call it like a integral reduction theorem. If it's bothering you, then the answer is yes. Again, the thing was muted, but not enough, I suppose. Okay, okay, so integral reduction theorem, and this is for one loop. Okay, and the theorem says the following, that if we're in d equals 4 minus 2 epsilon dimensions, and we want epsilon small, I think it's an experimental fact that epsilon is pretty small. Well, okay. Although I guess some will argue with that, but never mind. Okay, and what the theorem says is that if you have a one-loop amplitude, let's say an endpoint function, and this is now a general theorem, it doesn't matter what the theory is, it says that this is equal to a sum over integrals, and the integrals will have coefficients. So let me draw an integral. So this picture here is an integral. And what I mean by this integral is it's just the Feynman propagators, and then you do the loop integral. So that's completely standard. So there's nothing in the numerator. This is a coefficient here. This coefficient does not depend on loop momentum. So this is only external momenta. Or spinners, maybe spinners are better, right? That's what I showed you last time. Okay, so there's boxes, there's triangles. Again, it's a sum over these integrals, so you have to sum over all the possible ones. Triangle integrals, like so. And then there's a sum over all the bubble integrals, like so. And then there's plus, we'll call them rational pieces. So these are some extra pieces. And all of these guys, these are just rational functions. All of these b's, d, b, dc, and b, they're all rational functions. And if I make the theory massless, then there's no tadpoles in here. We can just forget about it. Okay. Now, the first place I'm going to say, don't worry, is right here. Don't worry about this. We're going to ignore this in the lecture. Ignoring this in QCD is hazardous to your health because it means you have the wrong answer. But maybe if we do supersymmetric theories, we're allowed to ignore that. Okay. Okay. And this is a basis of integrals. We'll call this the basis of integrals. Now, these integrals, these are, we call them scalar integrals. Let me write one of them down. So you see that there's no monkey business. It's just an honest-to-goodness loop integral. Although, let me put it over here. And let me put some labels here. So let's call this momentum K1, this one K2, K3, and then K4. And these are just a collection of massless legs all at this corner. Okay? So, so this can be some very high point. You know, it could be a 7 point, 8 point. But the integral we're talking about, this one here has only 4 corners, just the box integral. And it's just given by something we know and love. Okay, so this is just the Feynman integral, p minus k1 squared, p minus k1 minus k2 square, and then also down on the denominator. I also have p plus k4 squared. Okay, so now, in what I'm doing here, I'm going to be sloppy in one point. You see the d here? Right? This is dimensional regularization. D is equal to 4 minus 2 epsilons.
So what does the 2 buy you? What does the 2 buy you?
This?
No, the 2 and the 2 epsilon.
Why is there 2? I don't know. It's a convention. People used to use both. Sometimes they'd use epsilon and sometimes 2 epsilon. Then there was symmetry breaking, and now everybody uses 2 epsilon. It's just a convention. If I were to make it epsilon, I would always get it wrong in my lecture because I've been using 2 epsilon for the last, I don't know, 20 years. Okay, it's of no consequence, just convention. You know, it gets rid of 2's elsewhere. Okay, so I'm going to be sloppy in one spot. And you're going to see this throughout my lecture. What I'm going to be doing is I'm just going to ignore this. Okay? And we're going to ignore it because it makes things simpler. But at the end, you have to fix this problem. And essentially, I'm going to say, oh, it can be fixed. I'm not going to explain how you fix that. And this is going to be something important in my lecture, that we can make this actually 4 dimensions. Now, some of you will say, oh, but when you do that, then this thing is going to go infrared singular, and it won't make any sense, and blah, blah, blah. But never mind that. Don't worry about that. Okay?
What are the assumptions of this theorem?
Yeah. So this theorem it's this. This is the assumption that you're near 4 dimensions. Now, the way this theorem is proven has a lot to do with the following fact, that if you look at a pentagon integral, there are 4 independent external momenta, and you can use that to expand even the loop momentum in terms of those 4 external momenta because they form a basis, and then you can use that trickery to relate any pentagon integral to boxes and so on. Okay, but anyway, let's just accept this theorem. No, it's a theorem on integrals.
So enabling spin to particles?
Everything. So it's just a theorem about integrals. If I have some amplitude written in terms of Feynman diagrams, then the theorem tells you it can be expressed this way. Okay? So I'm going to use that, and I definitely don't want to spend time proving this, this theorem. So let's just accept this to be true. This theorem, by the way, has been known since 't Veltman and even before, yeah?
What are we actually summing over?
These are all the different integrals. So there's the legs here. Yeah, I should have been more clear. You see the legs? So they can move around. Like this leg could come here, and that's a different one, okay? So you have to sum over all these different integrals, okay? That's what, right. The question of what are the rational pieces is, in fact, the whole subject of the lecture. Because because these integrals here, they're all known. And they've been known for 15, 20 years. These scalar integrals, you see the one here? These are all known. The integrals which you could say are not known or much harder are the ones that, that might have some stuff up in the numerator. But this theorem basically tells you that all you need to do is figure out these coefficients here. It's called integral reduction, right? So if we get these coefficients, we've solved the problem because someone else has already done these integrals for us. Okay? That's rational. So anything that's rational, we can deal with. Okay. Yeah. Don't worry about. You mean this thing? Yeah. Don't worry about that. Don't worry about it. Actually, the rational pieces have to do with this here. It's exactly right here. This sloppiness right here is what causes those rational pieces. If you're not sloppy about this, you get those correct, okay? Yeah. Yes.
Maybe I can follow on that question.
Yes.
When we discuss non-rational, do we have in mind logs?
Yeah, these are if you do one of these integrals, this one will be a dialogue, okay? So these integrals are known. Yeah, I should have said that. You look them up. They're a set of polylogs. Okay? So the entire problem, and like I say, this theorem has been known since the beginning of time, since people have been doing these type of calculations, or some variation of these theorems, that the problem is to get these coefficients. And the integrals have been done already in the past, the integrals that we actually need. So our problem is entirely the question of how to get these rational pieces. Okay? So how are we going to do that? Well, obviously, yes? Yeah, it's a very similar. So for massive, it's similar. It's not identical. For example, you get tadpole. So there's now the theorem will include integrals like that.
Yeah, but the integrals have now massive propagators?
Yeah, massive propagators, right. So this is all massless. Oh, right. Something important, except for top, except maybe sometimes for bottom, at the LHC, all of this is massless. You can most definitely ignore quark masses. Even bottom, you can just forget about it. Okay, so massless is the problem that we really need to solve. Okay, and the other reason why I want to talk about massless is because it's obviously simpler. Okay, okay, so how are we going to do this? Well, we need to think about this in an on-shell way. We definitely do not want to write down these Feynman diagrams and then once we have the Feynman diagram, have some procedure called integral reduction that gets us here. We want to somehow do this from in an on-shell language without using any gauges, without using Feynman diagrams. Okay, so let's have a look at something more specific, like a 4-point amplitude. So what I'll be talking about, it's called the Unitarity method. Those of you who are old enough to remember the 60s will see an echo of the 60s in my talk, but it'll be a little bit different. Okay. Actually, there's a key difference between what I'll be talking about and what was in the 60s. Now, we know a lot about the analytic structure of these things because we, of course, have Feynman diagrams. So the Feynman diagrams, the existence of the Feynman diagrams, they guide a reorganization using ideas from the 60s. Okay. Okay. So let's look at specifically the 4.1 loop. Just as an example of what we want to do. Okay. So this thing, we can write it out. At 4 points, it's nice because there's only one box. So there's, let's put some labels, 1, 2, 3, 4. Okay, then I would have an integral like this, C1, like so. C2, like so. C3, like so. Okay, and these are going to be all the integrals. So, okay, and then there's two bubbles. And there's some coefficient, let's say C4 and B1, B2. Okay. So our goal is to go after these. Now, the basic idea of how to do this is you know a lot about the structure of the amplitude, right? So let's have a look in particular at some product of amplitudes. Okay, so these are two 4-point amplitudes like so. Okay, 1, 2, 3, 4. This is a tree amplitude, so this is a tree. And it's on shell. These legs, let's look on shell here. Okay, and this side, this also on shell here. Okay. And let's, I'm going to perform a sleight of hand. I'm going to say, let's ignore this for a minute. So you see the integral? Let's ignore the fact that there's actually an integral. Let's focus on the integrand. Okay, so this, so what I'm going to do is I'm going to try to relate this to this. So what I'm going to do is I'm going to look at all the contributions where these guys are on shell. And what do I mean by that? I mean that I am taking the propagator 1 over L squared when I cut it like that. And what I'm going to do is put it on shell. Okay? And with Feynman diagrams, there's something called Katkowski rule, so that's from the 60s, that use these ideas about cutting these diagrams and putting intermediate legs on shell. So I'm getting rid of the propagator before I go on shell. I turn it into an on-shell delta function. If I didn't get rid of the propagator, it blows up. It's infinite. But okay, and then what I do is I walk through here, and I find all the diagrams, this one, this one, this one, and this one, that can contribute to this product here. And I'm going to do it by ignoring this for a moment, right? Focus on the integrand, not the integral. So what I then expect okay, what I then expect is that this product of tree amplitude, so let's take a tree, and then let me put some labels on here. Let's put L1 this way and L3 this way. So I then expect that this product of amplitudes And, okay. This product of amplitudes can then be expressed in terms of this, these contributions here. Now, this contribution D1, notice that he's got propagators here. Let's call this L1, L2, L3, and L4. And then the same, I'll use exactly the same labels here. So this, here I have like an L4, here I have an L2, you know, and so on. Right? So I expect that I should have an equation that looks like this. So this is now an equation for those coefficients that I'm interested in terms of a product of amplitudes. Right? So now you can imagine that you can solve the problem something along these lines. You take this, you work it out explicitly, and you shake it into this form. Right? So you do algebra, like partial fractioning. So this would be one option, is you partial fraction. So left and right line up. Left, let's call it left and right, line up. And then you read off the coefficients. Now, this game is a little bit tricky because, you know, partial fractioning is probably not the slickest way to do it. There's also something I hid from you, which is, you see, there's an integral here. We're talking about the integram, but there's an integral. But sometimes things can integrate to 0. So then the problem is there could be some extra things I have to worry about on this side that integrate to 0 in order to algebraically solve that. But anyway, this technique actually works, and you can do that. But that's not how we're going to do it. We're going to do it in a much better way. Because you keep on staring at this word, on shell, right? Then you look at this and you say, hey, how come you left these guys off shell? Put them on shell. That's what you should do. So that's what we're going to do, and that's called the quadruple cut. And this is extremely neat. How come other speakers don't have this problem? I was pondering that question. Maybe I'll get the solution at some point. Okay. So what we should be looking at is more things on shell. More on shell. If we really want to solve this problem properly. And this would be the quadruple cut, the quad cut. So by the quad cut, I just mean that what we're going to do is if we're interested in, let's say, some integral like this, some integral like this, and we're interested in this coefficient, there's some coefficient here, d, we want this, what we should be looking at is the following cuts. So by this picture, on this side, I mean amplitudes. So this is an amplitude picture. And on this side, I mean integrals. And I want that coefficient that's sitting in front of the integral in the theorem. So the way I'm going to do it is I'm going to, if I'm interested, let's say this is L1, L2, L3, L4, I pick an amplitude where, let's see, that's K2, that's K1. Actually, if I draw them with the same number of legs, they even look the same. It's in one-to-one correspondence, right? This is an integral. This is an amplitude. So this could be non-local here. I mean, it's just an amplitude. Right? We put everybody on shell, but I do it in a way one-to-one correspondence. And now the observation is the following. Let's count. I have 1 on-shell guy, 2 on-shell guys, 3 on-shell guys, 4 on-shell guys. I have an integral, now being sloppy, right, which has 4 objects being integrated, and then I have 4 delta functions. Okay, so I don't know about you, but if I have 4 delta functions and 4 integrals, it's frozen. And notice again the sloppiness that I dropped the -2 epsilon. Okay?
Delta L squared. Delta L squared.
Delta, well, oh, so sorry, squared. I'm sorry. Yeah, of course. Right, so but anyway, it's 4 delta functions and 4 integrals. Okay, so this is frozen. So it's a rational function. And not only is it frozen, but these delta functions, I solve these delta functions in terms of external momenta. So then everything that's in here that's not corresponding to one of these propagators, so here I can again do the same thing, it winds up in that coefficient. So we solve what happened here. Yeah. So we solve the Li in terms of the Ki, and that gives us the coefficient. And the specific formula, so this was first written down by Brito, Cacciazzo, and Fang. You get this nice formula that it's 1/2, and then the sum over there's 2 solutions that you sum over. And then the product of 4 trees, 2, 3, and then 4. Okay, and then this is Li goes to Li solution. And these Li solutions, they're solutions of the on-shell conditions. So L1 square is equal to 0. I'm going to, again, like I say, it's massless, so I'm making it massless. L1 square equals 0. L2 square is L1 minus K1 square. L3 square, and that's equal to 0. And then L3 square is L1 minus, oh, the square is out here. L1 minus K1 minus K2 squared. And then L4, this is again equal to 0. And then L4 square is equal to L1 plus K4 square. And that's again equal to 0. So you just solve these equations, and there's actually very, very general solutions to this, even with masses. But what I'm going to do here is, instead of talking about the general solution, never mind that, I'm going to work out an example. It's, again, a non-trivial example, but it's completely trivialized by this formalism. If I want to know the coefficient of these boxes, I just put down amplitude, 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 solve these equations, plug in the solution, I'm done. That's the answer. Okay, now, if I'm doing it on the computer, then basically I'm done right now, because I can just solve these things numerically and then plug in the solution, I'm done. But generally, if we're doing it on the blackboard, like I'm going to do it, and I want an analytic formula, you know, I need a little bit of finesse in solving it in a nice way. Okay?
What is the deep reason that this prescription works? You can calculate the coefficient of this.
Well, it has to do with the analytic properties, that the only analytic function that you have, you see, I mean, yeah, this box is the only analytic function. This box integral is the only analytic function that has this propagator present, this propagator present, this one, and this one. So by matching, you could say, the singularities of this and this, by going to these on-shell conditions, we uniquely pick out the term. Now, in Nima's talk, he's going to be talking about leading singularities and leading singularity this, leading singularity that. And this is exactly what he's talking about. These things here are called the leading singularities, or we like to call them the maximal cuts. So they're you could say, a tool for picking out certain functions that have a specific analytic property. Okay, and because there's Feynman diagrams underlying it, we know all the possible functions that could occur. So there's no surprises. Like, oh, like in the 60s, you could say the problem was that they didn't know what analytic functions there would be. You know, it wasn't locked down by Feynman diagrams. But here, we're completely locked down in terms of, you could say, which polylogs and which specific functions appear. Okay? Okay. In fact, this part I'm talking about here, the way this box is done, is something very important for n equals 4 super Yang-Mills at high loop orders. The same basic ideas. Okay, so let's work out an example, a specific example. But I see I need to move along. Ooh. Yeah, I think I'm moving a lot slower than I expected, but okay. So let's do one loop, and let's do a 5 gluon amplitude. So for homework, you do all the trees. Okay, on the blackboard, I'm doing a loop now. So it's again one of these MHV amplitudes, and we'll make it pure glue. We're not making it supersymmetric, so it's the real thing that we would need at the collider. Would be a good example. And just to draw you the Feynman diagram. See, the Feynman diagram looks like this. And then, of course, many other diagrams, many hundreds of other diagrams mixed in there. Okay. 5. Oh. Huh. Yes, 5. Right. 4 is too simple. Got to do at least 5. Okay. Now, I'm just going to work out one coefficient of the box. And once you see how to do one of them, you can do all of them. The triangles, I hope to say a little bit about, although I'm probably running out of time. Okay. So, again, the idea is on shell. And let's just pick, so let's just pick one. Pick one integral. And I want to know its coefficient. How about this one? 1, 2, 3, 4, and then 5, like so. And I want to know this coefficient. Let's call this D1. It's the first integral, and I want to know what that rational function is. So what I'm supposed to do is, in correspondence to this, I consider unitarity cuts. Well, they're like generalized unitarity cuts, because we're cutting more legs. Basically, we're cutting every leg in sight. So everything is on shell here. So this is on shell. And then it's 1 minus, 2 minus, 3 plus, 4 plus, and then 5 plus. And then because if these are 2 minuses, then this guy here has to be a plus, that guy has to be a plus. Otherwise, this amplitude would vanish, right? That's an amplitude. Now I come over here. Because I have my all outgoing convention, if it's outgoing here, then it's incoming there. And then if I make it outgoing, I have to flip the helicity. So this one is a minus. Then I move along here. One configuration, I can have this plus minus, like so, minus minus, and then plus minus. I hope that's readable. That's one configuration. I have to go through all the different configurations of the different helicity contributions. And in fact, there's a total of 3 of them. Oops. So we can have another one. So these are, again, amplitudes. Okay, then another one. Okay, and this one, minus, minus. This is plus, plus, minus, plus, minus, plus, and then minus, minus, plus. We'll call this one diagram B. This guy we'll call diagram A, diagram C. And that's basically where you just flip this thing around. It's the same thing. It's the same structure as this one. Okay. Now you should know by now, if I'm going to write down more than one diagram, you know it's going to happen to 2 of them, right? They're going to vanish. So in fact, these 2 vanish, and let's see why they vanish. So let's look at this configuration here. So let's make this 5 plus. So this is this guy has 2 pluses and 1 minus. So that's anti-MHV. Now look over here. This guy here has 2 pluses and 1 minus. So that's anti-MHV. So let's have a closer look at what happens if you have 2 anti-MHVs next to each other, those 3-point guys. These 3-point guys, if you have 2 of them next to each other, let's see what happens. So I'm going to now write down the answer for that corner. There's one corner here. So that's L4 plus. There's 4 plus. L5 minus. So that's this corner here. And I have my label. I'll call this L4. I'll call this L5. OK, so I'm looking at this corner here. And then I'm going to do the same for that corner there. I'm going to write down what that thing is. So this thing, by our rules, it's minus L4, 4 with a square bracket, and then 4L5, again square bracket, L5 minus L4. Okay, and you notice it's in terms of the square brackets. But these are all on shell. All legs are on shell. So what does that mean about the angle brackets? The angle brackets have to vanish, right? So that's what I said last time, that either if you have a 3-point function with all massless, then either the angle brackets vanish or the square brackets vanish. So in this case, it's obvious that the angle brackets vanish. All right? So we therefore have, for example, L4, 4, that's 0, or 4L5, that's 0. Okay, and then let's just rewrite this guy here. Let's rewrite that in terms of 2-component notation. I'm sorry to say I'm mixing 4 and 2-component notation, but okay, that's, I guess it's bad taste, like Michael said. But anyway, we can write this in 2-component notation. And if we write this in 2-component notation, then this thing will be A4 lambda B, and then let's say L5. So what is this? And this thing is equal to 0. So what is this a statement of? This basically says that lambda 4 is proportional to this lambda of the L5, right? So this spinner is proportional to that spinner. That's what this says. So we're going to write the following. We're going to make the following observation, that lambda 4 is proportional to lambda L5. Okay. And now let's look on the other side here. On this side here, 5 plus. Okay, and then we have this thing is L5 again, but it's now the opposite helicity, because this thing about the helicities flip when you go outgoing or incoming. And then over here I have this is L1. And again, notice that this guy here, this is again an MHV bar. Both of these are MHV bar. Okay, so I don't have to write down the vertex, but from here you can deduce that lambda 5 is proportional to L5. So therefore, lambda 5 is proportional to L5, to lambda L5. So there's the second thing. So what does this mean? It means that this spinner, lambda 4, is proportional to that spinner. So that's our final deduction. Lambda 4 is proportional to lambda 5. Now let me ask you this. How can it be that this spinner, which is just some particle that's going out, is proportional to that one in general? And the answer is it can't be, because this particle is going this way and that particle is going that way. We're considering some general scattering amplitude. So except for very special kinematics, which is actually completely irrelevant, this is impossible. This is a contradiction. There's no solution. So there's no solution to the cut equations. This guy has no solution. Because these two spinners are not proportional to each other. They come from independent momenta. So they have nothing to do with each other. Okay? So there's no solution. So there we go. The contribution from these is irrelevant. Or not irrelevant. It vanishes. So I only have one guy to do. So I have to work this out. So let's work out that one contribution and see what the coefficient looks like. Yeah. Yeah, there's, what did I do? Hold on. Yeah, sorry, I was too quick. That's what I was. It looks like this. So that's a minus here. Okay. And the same argument goes through. Just MHV and MHV bar are going to get themselves changed. But anyway, the same argument goes through. Okay. So now we have one guy to do. So now what we have to do is do the A contribution. So we need to solve the on-shell conditions. Now when you have massless momenta around, it's actually usually pretty easy to figure out what the on-shell conditions, what the solution are. You see there's 3 massless legs here. So the fastest way to do this is to just stare at it for a while and then just write down the answer. So I'll proceed to do that. So let's solve the following. Let's put on some labels here. Let's make this L1, L3, L4, and L5. Okay? And let's solve L4 square is equal to 0. L3 square is equal to L4 plus K3 square. And L5 square is equal to L4 minus K4 square. Okay? And you stare at this for a little bit, and you see the solution is this. L mu is equal to 1/2 Xi. And this Xi, I'm going to figure out what it is in a minute. This is just a parameter that I have to solve for. And then it's 3 minus gamma mu 4 minus. So first of all, notice L4 squared equals 0 by Fiertz. That's the Fiertz that I used last time. And then if I do L4 plus K3, you might notice very quickly that I pick up L4, and then I get plus this 1/2 and then Xi, and then 3 minus K3 slash 4 minus. So this thing is just 0 because the Dirac equation kills it. Okay, and the same thing. So the same argument for here. So in fact, all of these are equal to 0. So that solves 3 of the on-shell conditions. I have one more on-shell condition, right? Because I have 4 propagators. This one, this one, this one. I've just put these guys on shell. I need to put this guy on shell, so I'm going to do that. So L1 square is equal to L4 minus, let's write it as K45. So K45 is K4 plus K5. Okay. Okay. So this thing, then I have to square this. I don't know if that's readable, but okay. So this thing is equal to minus, well, if I square, L4 squared gives me 0, so then I pick up a cross term, and then I also pick up the square of this thing. So the cross term is going to be minus C, and then 3 minus K4 plus K5. Oh, I don't know. Okay. There's like a dark spot on the blackboard here. Okay, anyway, that's a K5. And then 4 minus, and then plus. Let's call it S45. S45. That's a K4 plus K5 squared. Okay. So now I can set this equal to 0, and I can solve for Xi. So my solution then is that Xi is equal to 3 minus K5 slash 4 minus divided by S45. And I can just clean this up a little bit. First, I can write this as angle in square brackets. I can clean this up. So that's similar algebra as I did last time. And you just clean it up. You get 3, 5. Sorry, what'd I do? What'd I do? Something is upside down. Yeah, something is upside down. All right, what I should have done here, 1 over. Okay. Okay, let me write it. So that's equals S45, and then the 3 minus K4 plus K5, and then the 4 minus. Okay, anyway, let's clean this up, and then you get that this is equal to 4, 5 over 3, 5. Okay, so that solves it. So now you see I've solved all the loop momenta explicitly in terms of the external momenta. Because I know this parameter here. Where did I write it? L4, it's right here. Okay, times that parameter. Okay, so how do I then get the coefficient of the box, of that specific box? And the answer is I just write down the product of the 4 amplitudes, and I plug in the momenta. So let's do that. So the product. See here, I have. Well, I guess I erased it, but I need the product of. Let me write it down here again, because it's something useful. I'll put it right down here. I hope everyone can see that. 1 minus, 2 minus, 3 plus, 4 plus, okay, 5 plus. Okay, and then I have the following helicity configuration: minus, plus, minus, plus, minus, plus, and then plus, minus. Okay, and then the product that I have, the product of the momenta, these are the product of the tree amplitudes. It would be A tree, and then 4 point minus L1 plus 1 minus 2 minus L3 plus. And then second tree, so that's the tree down in this corner. Second tree is a 3-point tree. I'm going to quit writing tree. Let's just get rid of those trees so I don't have to write them. And then L3, 3 plus, L4 plus. That's a minus. And then another 2 of these trees. So I have A3, and then L4 minus, 4 plus, L5 minus. So I'm just writing down what that picture is. I'm not doing anything profound. L5 plus, 5 plus, L1 minus. And then the next thing I do is once I have knowing what trees I should put in, I just write down their values. Because remember, I know all the gluon amplitudes at tree level, so I just write down the value. And the value just basically using that Park-Taylor formula for 3 and 4, where it's, I guess, a little bit trivial. But anyway, we just write it down. And that would be, you see there's the 2 negative felicities here. So that would be a 1, 2 cubed. And then I write down 2 L3, L3 minus L1, minus L1, 1. Okay, that's the first amplitude. Second amplitude is, you notice it's an anti-MHV. It's 2 pluses and 1 minus. So that's in terms of the square brackets. So that's 3 L4 cubed. L4 minus L3. And then minus L3, 3. Okay, square brackets. And then let me just write it all out. Or maybe let me not write it all out, times 2 others. Okay, and this thing here has to be evaluated on the solution. The solution is right here. So this is now, all of this is to be evaluated on the solution. So now, you see, it's just a simple matter of plugging it in and then doing some cleanup algebra. So we plug it in. So we plug in so plug in the solution, and let me just tell you what you get. Now, one thing that you're supposed to use constantly is Li squared is equal to 0. Remember, everything is on shell. Whoops, no slash. Or Li slash. It's also equal to 0. Plug in, use this. And when you do that, you can quickly shake it into a form that looks like this. 1, 2 cubed, and then 4 minus L3, and then 3 minus, and then 4, 5. Oh, it must be for me. Okay. 2 minus L4, 3 minus, okay, 3, 4. And then 4, 5. Let me just write this out, because I want to just make one more comment about this. And then 4 minus L4, 5 minus. Like so. Okay, so, and this you just get basically by making the substitution and just combining things into the spinor inner products like this. Okay, so you got one more step here. You see this guy? or let me pick, let's say, like this guy here. So if I have 4 minus, and then L4, and then 5 minus, right, I need to evaluate this. But notice that L4 is in terms of spinor inner product. So what we do is we just expand it out explicitly. So there's the 1/2, there's the Xi, and then I have 3 minus gamma mu, and then 4 minus, and then I have 4 minus, and then gamma mu, 5 minus. Now this is exactly a guy that you can evaluate by the Fierz identity. See, this thing then is going to be 2 halves, that's 1, and then there's that Xi parameter that I solve for, and then you notice there's, well, anyway, when you do the Fierz, you just get this with 4, so it'll be a 3, 4, and then it'll be a 5, 4. Okay, so you can just go through and eliminate all these loop momenta like that. And then, anyway, that's the answer. In fact, let me just write down the final answer that you get so that if you actually do this for homework, which would be a good idea to fill in, I had some missing steps, but you should fill in the missing steps. So for homework, you can check that this is the answer you get. 1, 2 cubed, S3, 4, S4, 5, over, and then 2, 3, 3, 4, 4, 5, 5, 1. Okay, so this right here is the answer for the coefficient. Okay. Now, this is the example of boxes, how to do the box integral. So this is, you could say, just one piece of the problem. This technology, or this way of thinking about on-shell, makes this by far the simplest piece. It actually used to be that this was the most complicated piece to get, using older ways of doing it. This is now the simplest piece. Now, to get the rest of it, it shouldn't surprise you that it's a little more complicated, because the great trick in all this is that we happen to have 4 delta functions, on-shell delta functions, and 4 integrals. That means the integral is frozen, so you just basically plug in the solution and you're done. Yeah?
Is there a reason why it's so similar to the 3-level?
Yes, there are very good reasons for that. Nima will talk endlessly about that. Ask this to Nima and see if you can stop him. It turns out these, what we call the leading singularities, are closely related to pieces of tree amplitudes. So there's actually a very strong connection between the things we find here and the tree amplitudes. In fact, you can reorganize tree amplitudes in such a way that they're composed of exactly box coefficients. In fact, that's how this recursion relation was discovered, by looking at loops and then understanding that it looked like pieces of trees, and then there's some logic for getting it. So it's not an accident. Okay. So, but if you now go to the rest of it, it obviously gets more complicated for a very simple reason. If I'm interested in a triangle integral, there's a triangle integral that I want. Some triangle integral. Then we can just count. I have d4p, and that's again ignoring the dimensional regularization. And then I have 3 delta functions. Right? So that means there's one parameter left. Let's call that parameter t. There's some parameter that's not frozen. And then what you have to do is out of this triple cut. There's a triple cut that corresponds. Right, so you find the guy that matches this. What you have to do is you have to subtract out the boxes that you already computed, because you see inside here this is an amplitude. So for example, a blob like this, he's got, in terms of propagator structure, he's got two kinds of pieces in them, in it. Whoops, like this. And let's say, for example, if I were to insert this one in the top here, then you could see it opens up into a box. If I take this guy and stick it in there, it opens into a box. So I have to subtract those off. But those I already know because I already computed them. Right? And then the basic idea is what gets left behind up to terms that integrate to 0 is the triangle coefficient. And then again with the bubble coefficient, with a bubble it's the same story, except in the case of the bubble, we now have two parameters that are not frozen. So in the case of the bubble, there's two parameters not frozen. Right, so here's, if I'm thinking of a cut like that, then you see I have two delta functions. So 2 degrees of freedom are frozen, but 2 are unfrozen. That's 2 parameters, and needless to say, that's a little bit more complicated. But the place you should look this up if you're interested to see exactly how this works is a paper from Darren Ford. So you should look at this paper. Now this paper is not complete. It doesn't talk about these rational pieces that I dropped. But it talks about basically getting these integral coefficients. And then there's a paper from Badger. And there's actually many other varieties of this. I don't have the archive number from that. There's also papers from Brito and Feng. And anyway, there's a large number of papers that tell you how to use this on-shell technology for computing these integral coefficients at one loop. So in the remaining time, I see maybe I have 20 minutes or so. What I want to do is just show you some examples of where this is actually used, to do calculations for the LHC. So it's really to do calculations that would be, well, maybe the way I should phrase it is calculations that have not been done by Feynman diagrams, even though they're calculations that people have wanted to do for 20 years. Okay. Yes?
So when you do the triple cut, you also have to take into account the box? Because that's also
that's included. See, the triple cut, you could say, is I don't know where the word is. I don't know if the proper word is contaminated, but it contains box pieces in here. So if you just did the triple cut, you have pieces you're not interested in. But it's not so bad because you already know those pieces, so you can subtract them out. Okay. It's basically like a block diagonal problem that you attack by starting from the boxes. Once you know those, then you go after the triangles. Once you know those, you go after the bubbles, and then after that, you go after these rational pieces. Okay. Right. Okay. So I want to show you some examples of where this is used. First, actually, before I do that, let me amuse you. I can't resist showing you this. It's kind of amusing. So I'll give you another homework assignment, which you're welcome to do, but don't do it by hand. You see, the assignment would be do 5 gluons the way the textbooks tell you. So open up Peskin and Schroeder and just follow what they say. And just go ahead and do it with the standard Feynman rules, and ignore everything I said about the helicity variables or spinor variables or other fancier things. Ignore all that and just do it, right? So this is only a 25th of the answer, right? And this really is the answer. If you took out a microscope, you'd see dot products of momenta and polarization. So that, if you need any convincing that spinors are the right way to think about things, this transparency is it. This, all of here, it's contained in the Park-Taylor formula because at 5 points there's only MHV, right? So it's the same information, right? Okay, here's another kind of amusing thing. Let's suppose you wanted to do this tensor integral and you don't have all this on-shell technology. So this would be the way that you would do a Feynman diagram. You're doing the diagrams, you encounter an integral, you go do the integral. Hey, let's do the integral. By the way, this integral here, if you gave this to one of the professionals, let's say when they wake up, before breakfast they'd have it done. So this is not that hard for people who do this. This is, see, it's a 4-point function, right? So let's have a look what happens there. Anyway, that's actually the real result, no kidding. This is ground through a program called Form. So this is, right over here, right at that spot, is one of the basis integrals. And the coefficient of that basis integral is this mess. And it's just dot products of momenta. Okay. It's just some huge explosion. And then what happens is, well, for example, right here, I wrote, well, it's underneath there, but underneath the thing, I showed you one of the box coefficients. It just collapses, bang. So all of this stuff just cancels out in some very obscure way to generally give you much, much simpler answers than you might expect. Now, the problem happens if you take one of these, like you take 5, and you take one of these integrals, and then you put that together. So you're talking about high points, like we're talking about 6 points, 7 points, 8 points, right? Then the thing is out of control, and that's basically it's like a technical problem. But it's also tied up with the theoretical ideas of how we want to think about quantum field theory. Okay, what about applications? So let me show you some real life applications. So generally, we want to do some Feynman diagram calculation, and there's a whole machinery that explains why we're allowed to use Feynman diagrams for the description of the scattering of the quarks and gluons. Where's David? But anyway, he can tell you about the machinery. But the way it works is the diagram. Okay, so there's on this side there's the proton and there's some parton distribution functions and there's factorization theorems and all sorts of machinery. Then come the diagrams. Then come gluons and quarks, and these gluons and quarks they hadronize, and those are the jets. So in the experiment, when you see a jet, if you're a theorist, you could think, oh, there's gluons or quarks behind them coming out and hadronizing. Okay, so here would be an example of, for supersymmetry, an example of something that you would really like to understand in the standard model. So this is a very typical example of how you do a supersymmetry search. This would be a case of gluinos. So in the case of gluinos, when you just go through the basic supersymmetry, let's say you have two gluons. They come in, they like to interact with the gluinos. This is adjoint representation, so it's going to be a large contribution. Or it could be a large contribution. And then there's a cascade, and then out at the end comes, that's let's say an LSP. So this LSP, lightest supersymmetric particle, he is protected against decay, so he's just going to go out of the detector, disappear, and then you get missing energy. So the signal that you're looking for, typical signal would be missing energy plus 4 jets. But if you look at the standard model, you've got a problem because there's a process very similar to it. Z plus 4 jets. The Z goes to neutrinos, there's your missing energy. Notice that this is such a complicated process, you can forget about looking for any kind of mass peak. It's just at the tail of a distribution, there's going to be some excess. That's what you're looking for, okay? So what you want is to be able to control this in QCD. You want to be able to do, this is an example of what you want to do in QCD. So there it is, Z plus 4 jets. Okay, and this is now done, but maybe before I show you that, let me just show you where the Feynman diagrams are. So 1948, Schwinger did a 3-point function. And by the way, even late at night, I guarantee Schwinger did not use Feynman diagrams. But anyway, he had his, an earlier way of doing it. But anyway, it was a 3-point function. Let's go, we're going 60 years later, right? We have all the computer technology, and right, you can buy a supercomputer, you just need a little bit of money. And then, okay, after all the technological advance, this is the most complicated of these like W plus jets that's been done by Feynman diagrams. There's some other examples which are a little bit more complicated done by Feynman diagrams. But anyway, this is a flavor of where things stand. And the place we want to be is 2 more legs. Okay, but anyway, I'm happy to say, oh, no, before I'm happy to say something, let me just show you why in the world we want to do this. Why is this important? Right, so this is next to leading order QCD. This is not tree level, so it's next to leading order. So why do we want to actually do this? And I could give you all sorts of theoretical reasons. You know, I could start talking about scale dependence, that, oh, because we're truncating the series and we're only working to finite orders of perturbation theory, you get a residual renormalization scale dependence and factorization scale dependence, and that pollutes the calculation because there's like an uncertainty coming from not knowing what precise scale you're supposed to use. Or I could start talking about like the details of the jets are not included at leading order. There is a laser. Because at leading order, one jet is one parton, one gluon is one jet, so the structure of the jet is completely lost. If you go to next to leading order, then you get some real radiation, which then can fill out the jets. And then on top of it, there's kinematic constraints and all sorts of reasons. But forget all that. Here's the real reason. Because it's better. So this is like a classic example. So this is W plus 2 jets at the Tevatron. So it's a comparison of theory and experiment. And this is a program that's, it's called AlpGen. It's actually quite sophisticated. It includes parton showering. But anyway, it's pretty obvious there's some problem here. Okay, what's the problem? And you might say, oh, new physics, new, I don't know, resonance, new something, I don't know. But anyway, it's just that this is not good enough. Next to leading order QCD, out of the box, you see has really great agreement within error bars. Okay, and now this doesn't mean next to leading order QCD solves everything and we're just done, right? But this is one of the powerful tools that people use to make sure that they understand what the theoretical predictions are. If you get some kind of a blip or something, you want to know what's going on, then this is definitely one of the powerful tools in the arsenal. And I'll show you an example at the end. Actually, and here's a transparency I stole. This is from Gavin Salam at the ICHEP meeting. So that's the big experimental meeting talking about QCD, and he's talking about a QCD revolution. Actually, for this transparency, it's pretty hard to see what the revolution is. So you might be kind of amused. How long does it take people to add one more leg, right? And the answer is about 1 decade. So you go 2-to-1 processes done in the 1980s, 2-to-2 around 1990, 2-to-3 around 2000, and then, okay, 2010, we're sitting on 2-to-4 processes. And this is already after all the unitarity, that's the modern way. And also the traditional people, they've been working pretty hard too. So there's really been a lot of advance. But anyway, you see there's still a 10-year gap. Okay, this is really what the revolution is. See right here? 2-to-5. You do one, you do the next. And I promise you we're going to go on. It's definitely a breakthrough in our ability to do these types of calculations. Okay, so I just want to say a couple words, because These are actually quite complicated to do this. This is not, this is extremely non-trivial. This code, by the way, is 150,000 lines of code. So it's a little bit complicated to set all the bookkeeping and all sorts of issues you have to worry about. But anyway, that's a normal code, I would say, for next to leading order calculation. There's many more pieces, which I'll explain in a minute, than just this. There's some real radiation that you have to account for. But the basic idea is you put in on-shell tree-level amplitudes, and the output of this code is, again, numerical on-shell one-loop amplitudes come out. And that goes into the cross-section, yeah? 5. Oh, 5, that's what you mean. Okay. Okay. And actually, it turns out the expert on actually everything I've spoken about, and more than I've spoken about, he happens to be at Tel Aviv. And he's there this year. So if you want to understand more about how to do loop calculations and also the phenomenology of what's going on here, then he's your man. So he's going to be there in Tel Aviv for the rest of the year. This code, this particular one, this is the one I'm involved in, but there's lots of codes now. Everybody wants to do it this way, for obvious reasons. By the way, there's only one way to convince someone that you have a better way, and that's to actually do a real calculation and really show it. Otherwise, no one will pay attention. But anyway, now people pay attention. So there's a lot of codes being written, and based on these basic ideas. The actual calculation, I say, there's a lot of pieces to it because there's issues with real radiation. This is only one part of the answer. This is the plate, like the bottleneck. This was the problem, but there's other pieces which are pretty complicated as well. People knew how to do it, but it still takes a lot of work. And that, we get together with our friends in a program called Sherpa, which many of you may have heard of. If you're involved with LHC physics, you probably know about Sherpa. We work in harmony here, this Sherpa and Black Hat, working together on doing different parts of the calculation. I'm not going to really go through this, but just to point out that there's more pieces than just the virtual pieces. Okay, so here's an example. This is the calculation of Z plus 4 jets at next to leading order. There's Harold, our lead author on this. And this really is the best available theoretical prediction. So at this point in time, if an experimenter is interested in any kind of precision statement about Z plus 4 jets, then it's this program that they have to come to. Presumably that won't last long. Other people, I think, will do that. But best of all, here's a comparison against data. And this is done by the Atlas collaboration. So Atlas took our results. There's Black Hat plus Sherpa. They made various comparisons to other programs. You can't actually see so much here because the data, well, I guess the data is great, but the data does not distinguish between what different programs see. So this is in a test region. This is in basically using cuts where you're looking at QCD. You're not searching for supersymmetry, right? So here, a program has to agree with the data or the program is going to be wrong. Because there's certainly no new physics around here with the cuts in this particular study. The idea is then you take the program and you use that to help with the studies that are looking far out on the tails of distributions where they're looking for supersymmetry. Okay, so in this particular one, you better get agreement. Actually, kind of amusingly, there's this program Pythia that's a very popular program used constantly by the experimenters, and you may notice that the difference between the data is sitting here, and Pythia is like way off. But that's not a surprise to people who know how this works. Pythia didn't put in the right physics for this kind of physics, so it didn't come out right. But there's other programs, leading order-based programs. There's AlpGen and other programs which do quite well. We're basically all in agreement. Now, the purpose of next to leading order is, to a large extent, in order to see when the leading order programs are okay or where there's a problem. So it's all about reliability. So the reason why we do these precision calculations is all about reliability. And I'm almost done. Let me give you a real live example of how a theorist can really help the experimenters in a fundamental way, not with model building, but to really help them search for supersymmetry or search for new physics. Okay, and this is the following example, and this is from the supersymmetry search done by CMS. So in fact, this is the best search. So the key is to know the backgrounds, right? So you're not going to discover supersymmetry unless you really understand your background. At least not in any of the searches where you don't have some kind of resonance. So what you're interested in would be something like PP goes to Z, goes to nu bar, and then jets. Now, that you can't measure that. Experimenters, they like to measure backgrounds, right? I'm almost done. And experimenters like to measure backgrounds. So they don't trust theorists, period. They want to be able to measure it. So what they do is they measure something else. They measure photons. Photons are good because you get a lot of it, certainly a lot more than Z goes to mu bar. There's like a factor of 5. So here you have a lot more data. Normally, your statistics limited because you're pushing out as far on the tail as you can where there's very little data. So you're always trying to push up the amount of data that you have. So they want to use the photons. And then what you have to do is put in a conversion factor. Now, this conversion factor, to the dismay of the experimenters, there's only one place to get it from. It's from theorists. Because a Z boson is not a photon. You have to know what the conversion is. Now, Joey Candela, so he's the spokesman-elect of CMS, he approached us with the following problem. How reliable is that number? In fact, he wasn't even interested in the number. He just wanted to know how reliable it is. So they were worried that without theoretical input, maybe that number, the reliability, it's only 30%. Okay, so that's where you take out a next to leading order program and you start studying in some detail exactly what's going on. And in this example here, it's a comparison of different programs. It's next to leading order. This is a sophisticated leading order program, including parton showering. And you look at the ratio of Z bosons to photons. This is done with 2 jets here, but anyway, you can do more jets. And you look at the difference between them, and that difference is a measure of theoretical uncertainty. Had there been a large discrepancy between leading order and next to leading order, you'd worry that maybe things aren't under control. And in fact, it turns out there's a lot of things to worry about. So there's endless things you have to worry about. It turns out, for example, electroweak corrections, it sounds like they're very small, but out on the tail of distributions, as you're pushing up energies, it's possible to get large logarithms, and then all of a sudden electroweak is very big, so you have to worry about that. A simple question like, what's the electromagnetic coupling constant that you're supposed to use? It turns out half the experts get it wrong, and half the experts get it right, and there's like a 7% difference in those. So you have to worry about even an elementary question like that. I can assign that for homework. In this particular case where you have a real photon coming out, what's the value of the electromagnetic coupling constant? Is it 1 over 137 or is it 1 over 128? Anyway, you can ponder that question. And that's important because we told the experimenters that we have it under control to 10%, right? And if you're off by 7%, well, that's not so good, okay? And in fact, this study, this is the best constraints on supersymmetry in this paper. And like I say, the key point, why we do this, it's all about reliability. So when there's some problem with the experiment, either they come to us and they need to know, how reliable a theoretical prediction is, or if there's something funny is in the data and you're trying to understand it, then this is where you use next to leading order QCD. And of course, Well, one day we'd like to go beyond that. But anyway, but at least at this point in time, this is definitely one of the very useful tools for understanding LHC physics in multi-jet environment. So it's like I say, for solid theoretical uncertainty. If you want to go for more final state objects, that's where these new ideas are making a real difference that our experimental friends really appreciate. And the key thing is that this technology allows you to get results that would be very hard, if not impossible, to get in other ways. So it's like I'm trying to tell you, it really works. Okay, thanks.
Any questions?
Okay.
You understood everything?
Right.
What? You asked for tutorial? Okay.
Yeah.
Maybe I can
When is the tutorial?
What?
When is the tutorial?
at 6, I think.
Oh, yeah. Okay, well, yeah. Yeah, then we'll talk about trees. And I guess next time we'll have more fun talking about n equals 4 super Yang mills.
5:30.
5:30, okay.
What we only see, okay, there is a lot of people who are making standard calculation, right?
Who do, yeah, there's a lot of, yeah, there's often,
So how far away is the event and okay, what else?
I'm sorry,
How far away, okay, people who are doing, because there are thousands of people, I think, who are doing on computer standard book calculation.
yeah, not thousands, but yeah, there's,
500.
well, as it's turning out, day by day there's fewer of those. But there are still some, yes.
But they will cover yet the whole range of the things which is needed for LHC.
Absolutely not. Z plus 4 jets is the prime example. It's going to be a long time before Feynman diagrams can do that, I think. I mean, there's, of course, a lot of new ideas, and people have ideas and so on. So there's finite time. You know, sooner or later, you know, people will figure out even better ways. But as of today, this is clearly the best way.
More questions?
Okay.
Maybe I can ask.
Yeah.
So now you've been able to reduce the problem of calculating these amplitudes by, instead of hundreds of thousands of diagrams, you can do it with only a few boxes and
Well,
techniques with
yeah.
computer programs and like that. So
Yeah.
where will the next bottleneck will be?
Well, real radiation could be a problem to deal with that properly. Yeah, I would say that the current, like to go on, it would be better ways of dealing with the real radiation, and the next frontier is pretty obvious. Now that next to leading order QCD is basically, you know, being beaten to death with all these new ideas, obviously next to leading order QCD. So I think in the coming years, there's going to be a lot of work on applying these on-shell ideas to do two-loop QCD and beyond, you know.
What kind of calculations can we do with external quarks?
It's all included. You know, if you didn't do external quarks, our experimental friends would be very unhappy. They'd say, come back next year. No, it's all, I mean, you could say a lot of, you know, the complexity has to do with the bookkeeping. There's a lot of bookkeeping that you have to keep track of, all the different sub-processes, all the different, you could say, color objects. I mean, things are color ordered, but, you know, there's all sorts of different objects associated with each color factor. There's, anyway, some bookkeeping problem to keep track of all this. I mean, that's what the computer program is doing, or a substantial fraction of it. Yeah.
Why in the integral basis you don't have also diagonal twisted legs?
Oh, it's because I color ordered. I slipped that in before, while you weren't looking. So it's the color ordering I discussed in the last lecture. So in a sense, the twisted legs, you see, at one loop, twisted legs are really trivial because a twisted leg is like an untwisted leg with a relabeling. It's at higher loops that the twisted legs make a big difference, non-planar and planar. But at one loop, everything is planar, and if you're discussing one ordering, it's equivalent to discussing some other ordering. Yeah.
Yes. Have you talked to any computer scientists? Are there any connections to maybe complexity theory?
Not really. There are some of us, not me, but who work on, on Black Hat, who are pretty good with computer science and computers. One thing is that these algorithms of how it works, like the on-shellness and all, it's like it has a lot to do with the physics. So it seems hard how these ideas, carry over in that direction. Maybe in the opposite direction, that somehow the computer scientists help us. That I can believe. But certainly, for us to say something about that, I don't think that's going to happen, because it depends so much on like the details of the physics of what exactly you're trying to do, and so the algorithms are designed around, you could say, physical intuition about what the S matrix looks like and the structure of the S matrix, and that I don't see what a computer scientist would learn from that. I don't know which direction you were asking the question, us learning from them or them from us, but okay, either way, they're not going to learn from us. I think that's.
You mentioned doing next to next computing order.
Yeah.
Aren't we down to where the theoretical uncertainties are smaller than the uncertainties in part-time distribution functions?
Well, no, it's actually kind of the opposite. That by doing next to next to leading order, you can improve, for example, part-time distribution functions, right? So, the fact that let's say there's errors in the part-time distribution functions is not a problem. It's something that's good, because that is an argument of why you want next to next to leading order. And in terms of the part-time distribution function and the evolution, that is already done at next to next to leading order. The formalism for that exists, and all the calculations are in place. What's missing, you could say, would be more processes to use to feed into next to leading order part-time distribution functions. So it's an opportunity, not a problem. That's the way I would put it. Okay, anyway. Mm.